Let us look at semi-direct product of groups. In the previous session, we saw direct product of groups. So given two groups N and H, semi-direct product G is equal to N times H. So here the symbol for semi-direct product is this. N times H combines N and H such that H acts on N. Remember, in direct product of groups, they do not interfere with each other. But here, H acts on N. Now, G forms a new group where N is a normal subgroup of G and H is a subgroup of G. Elements of G is of the form N comma H ordered pair with N in the group N and H in group H. Now, we want N to sit inside G as a normal subgroup and H be inside G as a subgroup. We also want to write every element of G uniquely as NH with N in N and H in H. And we want H to act on N. So we define phi H maps to the automorphism of N. So that means phi of H maps an element of N to an element of N by doing something using H. So here an element of N maps to phi of H of N, and the operation in G is N1, H1 times N2, H2 is equal to N1 times phi of H1 of N2, H1, H2. So you see H1 is making some change to N2, or because of H1, N2 is changing in some form. Now because H acts on N via phi, conjugating an element of N by an element of H gives element of N. So let's take a deeper look at this. Consider N in N as the ordered pair N comma the identity of H. Now this ordered pair is in G. Consider H in H as the ordered pair the identity of N comma H, again in G. So let's do the conjugation. H N H inverse will give us what? H is En comma H times N. N is N comma EH times En comma H inverse. Now let's multiply the first two. So using this operation of G. So the first element En, phi of H of N comma H times EH, and this comes as it is. So we have multiplied the first two factors. Now let's multiply these two. Of course, before that we will simplify it. So En times anything will not make any change. So we don't write it. Phi of H of N as it is. Then H comma H, because H times the identity of H gives us H itself, times En comma H inverse. So this step is basically simplification of this. Now let's actually multiply these two. So phi of H of N as it is, then phi of H of E sub N, comma H times H inverse. Phi of H of N times En, comma EH H times H inverse is EH, which is equal to phi of H of N comma EH. What this does is this guarantees that N is a normal subgroup of G. Now, here remember phi of H is not an element of N, but an automorphism N to N that is applied to N in N. H sits inside G as the ordered pair E sub N comma H, where H is in H. Multiplication of two such elements is En comma H1 times En comma H2 is equal to, again using this operation we calculate. So En phi of H1 of En comma H1 times H2. Now here it is phi of H1 En times En. So it is En comma H1 H2. So basically this shows that H is a subgroup of G. This is pretty abstract, right? Because what we have shown doing all this is that N is a normal subgroup of G and H is a subgroup of G, and basically we have combined N and H to form G. So let's look at an example to understand it much better. Now let's take N equal to Z3, addition modulo 3, and H equal to Z2. Now let G is equal to N times H, semi-direct product. So elements of G are ordered pairs where N is in N and H is in H. Group operation, we have just taken this as it is. Phi maps H to the automorphism N. Now automorphism in N is equal to the identity comma alpha. So identity will take the elements of N and give the same thing back. So ID of 0 is 0, ID of 1 is 1, ID of 2 is 2, where 0, 1 and 2 are in N. Whereas alpha will not change the identity itself. So alpha of 0 is still 0. But alpha of 1 will be equal to 2. Alpha of 2 will be equal to 1. So basically it is flipping this. So again where 0, 1, 2 are in N. So here if H1 is equal to ID, no change. Why? Because phi of ID of N2 is equal to N2, which basically becomes a direct product. Now, if H1 is equal to alpha, it flips. That is, phi of alpha of N2 is equal to minus N2. This group operation becomes now N1 comma H1 times N2 comma H2 is equal to, now being specific to Z3, Z2, we will have N1 plus phi of H1 of N2. Because remember, group operation is addition modulo 3. So N1 plus phi of H1 of N2 mod 3, comma H1 plus H2 mod 2. If H1 is even, H1 is equivalent to 0 mod 2. If H1 is odd, H1 is equivalent to 1 mod 2. Or we can combine these two and say minus 1 to the power of H1. So see here, minus 1 to the power of 0 will give us what? 1. And minus 1 to the power of 1 will give us minus 1. So the operation becomes N1 plus, instead of writing phi of H1 N2, we can directly say minus 1 to the power of H1 times N2 mod 3 and H1 plus H2 mod 2. So if we substitute the values of Z3 and Z2, we get 0, 0, 1, 0, 2, 0, 0, 1, 1, 1, 2, 1. So G will contain these elements. Now, components interact via the action of Z2 on Z3. H is Z2. So H is acting on the elements of N. So Z2 on Z3. So the first component is manipulated by the second, and in the process induces an asymmetry. Due to this induced asymmetry, the semi-direct product is non-abelian even though Z3 and Z2 are abelian. So this was an example using Z3 and Z2. By taking the semi-direct product, we have arrived at the group G, in which N sits as a normal subgroup and H sits as a subgroup. And we also want to write every element of G uniquely as NH. Yes, that also we have done. And we want H to act on N. That also we have done. Let's take a slightly different example. Now, normally semi-direct product is used to find a larger group G containing given two groups N and H, where N becomes a normal subgroup of G and H becomes a subgroup of G. So what we'll do is we will take up a group which we are already familiar with and go backwards. So let's start with a bigger group B3. Now here let's take N, a normal subgroup generated by R. This would generate E sub N, comma R, comma R square. And we know it is isomorphic to Z3. So we can say N is a normal subgroup of D3. H is the subgroup generated by S, which gives us E sub H, that is the identity of H, comma S, which is isomorphic to Z2. And H is a subgroup of D3. So since we already know this, I have mentioned it. Okay. Now, phi maps H to the automorphism in N. Automorphism of N is equal to ID, comma alpha, where alpha of R is equal to R square, right? Alpha of R equal to R square. But if we say alpha of R square, what happens? It becomes R to the power of 4. R to the power of 4 becomes what? Becomes R. So that is R maps to R square and R square maps to R. That is generator to generator. Now, phi of S of R to the power of K is equal to alpha of R to the power of K, which is equal to R to the power of minus K mod 3. Phi of alpha, see here, this was general statement. Now, phi of alpha, ID and alpha, we have two options. So, phi of alpha of En is equal to En. Phi of alpha of R to the power of 1 is equal to R square. Phi of alpha of R square is equal to R. Phi of ID of En is equal to En. Phi of ID of R to the power of 1 is equal to R. Phi of ID of R square is equal to R square. So phi of ID will not make any change to the values of N. But phi of alpha will flip the generators without making any change to the identity. So R to the power of K, comma S to the power of L, because remember these are rotations and S are reflections. So we can rotate it any number of times. We can, reflect any number of times. So to keep it general, I'm taking it as R to the power of K, comma S to the power of L times R to the power of M, comma S to the power of M is equal to R to the power of K, phi of s to the power of L of r to the power of m, comma, s to the power of L, comma, s to the power of n. This is equal to r to the power of k times phi of s to the power of L of r to the power of m, comma, s to the power of L plus n mod 2. Now here, phi of s to the power of 0 is equal to id and phi of s to the power of 1 equal to alpha. So if we carry out these operations with the element that we have arrived at, we would end up with D3 equal to n times h containing elements r to the power of I, comma, s to the power of j, where I is equal to 0, 1, 2 and j is equal to 0, 1. So D3 is equal to n times h is equal to the ordered pairs E sub n, comma, E sub h, r, comma, E sub h, comma, r square, comma, E sub h, comma, E sub n, comma, s, comma, r, comma, s, comma, r square, comma, s. Finally, this can be written as D3 is equal to En times Eh, that is the identity of D3. R times Eh is r square times Eh is r square, En times S is S, then we have Rs and we have R square S. This is the group formed by the semi-direct product of N and H. And in the previous example, we saw the semi-direct product of Z3 and Z2. So if we do the comparison, we will arrive at the fact that D3 is isomorphic to Z3 times Z2, where here times means semi-direct. Now, while I didn't multiply two of these elements, ordered pairs, to arrive at this. I have directly shown it to you. So let me just show you two such examples. So here, let's take r square from n, comma, s to the power of 1, that is reflection once. This is rotation twice, rotation by 120 degree, times r to the power of 1, comma, s to the power of 1 is equal to, and we carry out these operations and we end up with r, comma, e, one of the elements. Similarly, r to the power of 5, that means rotating it 5 times, comma, s square, that is reflecting it twice, times r cube, comma, s cube. Again, evaluating this, we get r square, comma, s. So r square, comma, s. So this is just to give you an idea of how I arrived at this. So that was semi-direct product of groups. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.